Our next speaker, who you will quickly detect is not from around these parts, is going to be speaking about some research that's happening in the other part of the world.
Thanks, Dave. Hi, I'm Monique. I'm a visiting researcher from Sydney, Australia, and I'm working with the Marine Mammal Research Unit for a couple of weeks here. But I thought I'd switch it up a little and not talk about a BC marine mammal and instead give you guys some insights into some of the physiology from the Australian guys that I've been working with. So just a little bit of background. Oops, I've gone too far already. So I'm working with 3 species of otariid, or otariid, as you say in North America, I believe. The Australian fur seal, the New Zealand fur seal, and the Australian sea lion. All of these guys were hunted to near extinction in the late 1800s and have since experienced different rates of recovery. The Australian fur seal has generally recovered. The New Zealand fur seal is expanding its population and is starting to move into territories that were previously held by the Australian fur seal and the Australian sea lion. But our poor old Australian sea lion over there is endangered and is in decline at the moment. And these different rates of recovery are really interesting for management purposes, and we're wondering if physiology can maybe explain some of these things. So fur seals and sea lions have to travel really long distances and dive to great depths in order to obtain their food. And these have large energetic costs. But these costs differ across taxa and within species, particularly across the different life stages. So the aim of our project was to identify how the energy requirements might differ between and within the Australian otariid species. So how do we go about doing this? Aaron actually just gave a pretty good rundown of it, but I thought I'd show it to you instead. So this is Ronnie. He's a New Zealand fur seal housed at Taronga Zoo in Sydney, Australia. And at the moment, we're taking a measure of his standard metabolic rate, which is where he sits in the respirometer until we get a baseline measure. After that, we ask him to swim laps of the pool to measure his active metabolic rate, at the end which he'll return to the dome, and we can get an estimate of active metabolic rate. And as we know how long they swam for and the size of the pool, we can estimate speed, which we use for our cost of transport measurements. And cost of transport we're using in this case because we're really interested in how much energy they have to expend to get to their foraging grounds. We conducted 318 trials with the 3 species that I already mentioned, and in my study sample I had 11 seals. So some results. We found that there is indeed a decline of metabolism with age. I was lucky enough to have 5 female Australian sea lions in my study. There is actually 2 here, even though you can't really see it. But the great thing about this was they're the same age, around about the same weight, and they had the same metabolism. So I was very excited because it validated my results. Then we wanted to have a look at how the metabolism might differ across the different cohorts that I had. So I had some quite unique cohorts, including doing some of the very limited amount of physiology on males, which hasn't really been done before. But as you can see here is looking at the adults, we get roughly about the same metabolism across those 3 adult species. But when we add in the subadults, you can see that they're consistently higher than the adults within each of those cohorts. And then if we add in the active metabolic rate, this effect is exacerbated. Then we wanted to look at cost of transport. So the open squares in each of these graphs are the subadults of the species, and then the closed squares are the adults. And the main things to take away from this are that, again, we can see how much higher the cost of transport is for subadults as opposed to the adults. But also that when we look at the adults, we can see that the optimal swimming speed, and speed is along the x-axis here, is between about 1.5 and 2 meters a second. And this was also good for me because it validates some of Dave's research, or my research was validated because it's around about the same time as, around about the same speed as Steller sea lions, sorry. So what did we find? So we found that age matters. So as seals get older, their metabolism is declining, which can have really important management implications as this may be a vulnerable group that we may need to start looking at. And fur seals and sea lions reach physiological maturity really late. In the phosid seals, they actually get weaned a lot earlier than otariids do. And this can have this can have implications for their management as well, because if they're maturing really late, it means that they've got higher energetic costs for longer. So species did not really make a difference, and it seems as though metabolism remained constant across the species. So what does this actually mean? I've got to do some more research. So I'm currently looking into how season affects the animals, also looking at how gender affects metabolism as well. And hopefully I'll see you guys soon to tell you some more about it. Thank you.
For Monique.
I'm gonna run away.